Good morning. This is your stats sensei, Mr. Spensei, and we're going to be going over the Unit 3B test corrections. Please remember, if it's written in red, you need to write it down. Plus, anything that I write down on sticky notes or add to the paper also need to be included. So here we go. The distribution of weights for female cross-country runners is approximately normal, with a mean of 122 and a standard deviation of 8. Well, as soon as they tell me that, I need to be drawing my graph. And they're telling me, okay, it's normal. And they're saying the mean is 122. And I'll make a note to myself, the standard deviation of 8. Standard deviation of 8. Of course, this goes to positive infinity. And this goes to negative infinity. And it says, which of the following is closest to the percent of runners who weigh between 114 and 138? So we're looking at 114 somewhere here, and I'm looking for 138. And we're looking for this area right there. All right, they've told us this was normal, so I'm going to be working with the norm CDF. And specifically, I'm going to start off by writing norm CDF lower equals 114, upper equals 138, mean is 122, standard deviation is 8. All right, but I need to work on showing all my work. So probability statement 114 is less than 138. Well, we need to create a Z statement. So there's my Z formula. And the probability Z is less than 138 minus the 122. And let's go ahead and calculate that out because it's going to be a stat test Z test. So to do that, stat test Z test, our mean is 122. Our standard deviation is 8. The X that we're looking for is the larger one, which is 138. That's where we start. We're only looking for a singular value, so N will be 1. And we have a less than. We calculate. And that is a Z-score of 2. So we want the probability Z is less than 2. Minus the probability that we're going to go back and calculate this one. Stat test Z test. And of course, the X is 114. And we get the probability that Z is less than -1. So now we have all the statements that we need, and we need to do the calculation. Well, there are a couple ways to do this. So second vars, norm, CDF, lower bound, 114, upper bound, 138, mean, 122, standard deviation is 8. Press enter. And we get 0.818. So this equals 0.818. And my closest answer to that is D. That is one way. The other way you need to be aware of is we created these Z-scores right here. So let's take a look at those. All right. So with those Z-scores, we have the norm CDF. You also need to include this lower equals, the lower equals -1. The upper is 2, because this has a Z-score of -1. This has a Z-score of +2. All Z-scores are centered with a 0 and 1. So mean equals 0, standard deviation is 1. So second vars, normal, CDF, lower, in this case, be -1. Upper is 2. All Z-scores 0 and 1. There we get 0.818. All right, so that takes care of number 1. Kind of a lot of writing on that one. So I'll leave it there for just a half a moment. You probably need to pause so you can get that copied. All right, here we go. Looking at number 2. At a certain store, the distribution of weights of cartons of large eggs is approximately normal with a mean of 26 ounces. Based on the distribution, which of the following will contain the greatest proportion of eggs at the store? Well, if I subtract this, I get 4. And I subtract these, I get 4. And these are 4. And these are 4. So all the distributions have the exact same interval widths. Well, the interval widths are the same. And remember, our normal curve is mound shaped or bell shaped. And if this is my mean, the greatest area will occur in the center. So my greatest area, because this is the tallest part, will occur in the middle. And so we'll go, all right, 2 ounces below, 2 ounces above, that will have my greatest percentage. So 2 ounces below 26 is 24. 2 ounces above 26 is 28. There's my greatest area. My answer for this one is C. All right. All right, number 3, based on records kept at a gas station, the distribution of gallons purchased by consumers is skewed to the right with a mean of 10 gallons. All right, that's very important. So we're talking about skewed. We also have a mean equal to 10 and a standard deviation of 4. Awesome. A random sample of 64. Ooh, the random sample. This tells me my N, in this case, equals 64, was selected and the sample mean number of gallons was recorded. Suppose the process of selecting a random sample of 64, so there's that random sample again, and recording the mean is repeated for a total of 100 samples. Which of the following is the best description of the dot plot created from the sample means? All right, so we're talking about the sample means. Well, the distribution of the sample means is normal by central limit for n greater than 30. In this case, n equals 64, which is greater than 30. So it's normal by central limit theorem. All right, so we're talking about normal by central limit theorem. The mean is the mean is the mean, so that's 71,500. Our mean didn't change. All right. And the I'm sorry. The mean is in this case not 71,500. The mean is 10 gallons that we had up above. All right. And their standard deviation is 4 divided by the square root of 64. So 4 divided by 64 raised to the half power is 0.5. All right. Now we do not worry about the number of times we repeat it. We worry about the sample size. And they told us the sample size is 64. Most people who miss this problem divided by 100. We don't care about the number of times you repeated it. We care about the sample size itself. All right. Number 4 may be the most missed problem on this test. For a random sample of 42 rabbits with a mean weight is 5 pounds and the standard deviation is 3, which of the following is most likely true about the weights for the rabbits in the sample? All right, so let's talk about this distribution and decide what it is. And by the way, this says true about the weights. This is not talking about the distribution of the means. Nowhere does it mention distribution of means, distribution of X bar. So we need to talk about the distribution of rabbit weights. Well, if I draw this picture, it's like, okay, they told me it's normal. Or they didn't tell me it's normal, but I'm going to start off and act like it is. Because I know we want to sit there and go, hey, we have a sample size greater than 30, but it says, let's say mean weights. It just says the weights. So the average weight happens to be 5 pounds. And they tell us the standard deviation of the weight is 3. So that's 1, 2, 3. So this is 8, 11, 14. That's a big rabbit. 1, 2, 3. This becomes 2. This becomes -1. This becomes -4. Hopefully I did that right. All right, so when I look at this, the very first thing I go is, well, 0 is somewhere over here. I can't, and that means the only way I can have are going this way. It's like, oh, that's no longer normal. I'm missing the, I'm not 3 standard deviations. I don't have 3 standard deviations below. I may have 3 standard deviations above, but I don't have it below. So this is going to be skewed to the right. So I end up with a distribution that's skewed to the right. And the reason is like, oh, my lowest value is 0. That's, I can't have a weight less than 0. So if I have z equals x minus mu over sigma, I go, well, that ends up being 0 minus 5 over the standard deviation of 3. And when I do that, I find out that I can't be, I mean, there's no way I don't have enough standard deviations below it. Because when I look at this, it's like, oh, we're less than 2 standard deviations below. We're only 1, well, what are we? We'll calculate that. -5 divided by 2. -5 divided by 3. So 1.67. So z has to be greater than -1.67. I've written my z-score. I cannot be more than 1.67. And that's with a 0 weight bunny, and we're not going to have a 0 weight bunny. So this is skewed to the right. So when I look at this, the distribution of the sample values always follow the distribution of the population, because we asked about the sample values, not about the sample means. And the smallest weight is less than 2 standard deviations below the mean. Matter of fact, it was 1.67. All right. So when we're looking at this, we're looking at C. All right, number 5. This is also another problem that was missed a whole great deal. 3, 4, and 5 are the most missed. There were 5,317 previously owned homes sold in a Western city in the year 2000. The distribution of sales prices of these homes was strongly skewed. All right, so we have an underlying distribution that's skewed with a mean of 206,000 and a standard deviation of 37.8. If all possible simple random samples of size 100, so n equals 100. In this case, they're telling me the standard deviation equals 37,881. Mean equals 206, 274. From the population and the mean is computed for each of these samples. Which of the following describes the distribution of the sales price of the sample? Look, describes the distribution of the sales price. It did not ask for the distribution of the sample means. It did not ask for the distribution of X bar. Distribution of X bar in this case would be normal by central limit theorem. Distribution of means, normal by central limit theorem, but it did not ask for that. It asked for the distribution of the sales price. The distribution of the sample, so that's the distribution of the sample, which will always follow the underlying population. The underlying population is skewed, so we're going to have a skewed sample, and we'll have a skewed sample with a mean equal to the mean, because the mean is the mean, and our standard deviation is 37,881. The distribution of sample values always follows the distribution of the population. All right, it's only when it has the X bar or distribution of the average or distribution of the means that it becomes normal by central limit, or approximately normal by central limit. A sleep time of 15.9 hours per day for a newborn baby is at the 10th percentile of the distribution of sleep times for all newborn babies. Assuming the distribution is normal with a standard deviation of 0.5, approximately what is the mean sleep time in hours for the newborn baby? All right. They tell us it's normal. That's the word I was looking for. All right. Well, they told me it's normal. As soon as they tell me it's normal, I'm drawing a picture. There it is. All right. And they tell me that we have the 10th percentile, which is this area right here. And they tell me that that is 15.9. They don't ask me, they don't have the mean. They're asking me to find the mean. And so I write down z equals x minus mu over sigma, and I start plugging in what I have. And what I see that I have is I have 15.9. I know I'm looking for the mean, so I don't have that. All right, they tell me the standard deviation is 0.5, so I'm plugging in this. And I have a problem. I'm missing the mean and I'm missing z, but they gave me an area, at which point I can go second vars inverse norm. So inverse norm. I go to the inverse norm thing and go, what is it asking for? Area. In this case, area equals 0.10 because it's a percentile rank, and we know percentiles ranks go from left to right. And we have a z-score, so mean equals 0, standard deviation is 1. So I've gone to area, inverse norm, and I go 0.1, mean is 0, standard deviation 1. And I calculate, and I get negative 1.28. And I'm going to solve, from this point, I'm going to solve by algebra. So I'm going to multiply times 0.5. And then I'm going to subtract 15.9. And I end up getting negative 16.54 equals negative mu multiplied by negative 1. They'll both become positive. And with this particular one, 16.5 is my closest answer. All right. So this one is D. Number 7, a blind taste test will be conducted with 9 volunteers to determine whether they can taste a difference between bottled water and tap water. Each participant will taste the water from the 2 different glasses, then identify which glass he or she thinks the tap water, assuming the people cannot taste the difference. So if there is no difference, the probability that you're going to guess it is 50%. There's 50% chance you get it right, 50% chance you get it wrong. So in this case, we have a probability of guessing equal to 0.5. All right. And it says, what's the probability that at least 8 of the 9 participants will correctly identify the tap water? Well, first off, we have a group, and we have a fixed probability. And since we have a group, this is going to make it a binomial CDF. And so they said at least 8 of the 9. So that means I'm looking for this. All right. So work shown. Well, there's my probability statement. Probability x is greater than 8. 9 choose 8, 0.5 to the 8, because that's our probability. 1 minus that, 0.5. 9 minus 8 is 1. Then we also have to have a 9 choose 9, 0.5 to the 9, etc. For the calculator, I'm going to have to do we subtract out what we don't want. So we're going to have a 1 minus binom. Anytime, and the reason it's 1 minus because we didn't circle the 0. If you don't have the lowest value and you're working with the CDF, and you're always working with the CDF if you have more than one value or it's an at least. 1 minus the binomial CDF, trials equals 9, probability 0.5, x equals, well, I need to be careful. I want 9, I can't subtract it out. I want 8, I can't subtract it out. I always subtract out the highest value I don't want, which in this case is 7. So 1 minus, here, 1 minus second bars binomial CDF, trials is 9, probability is 0.5, x value is 7. And there we get 0.0195. And our closest answer is B. All right, number 8. The caffeine content of 8-ounce cans of a certain cold drink is approximately normal. Awesome, so let's draw a curve. With a mean of 33, a random sample of 8-ounce cans, randomly selected 8-ounce can, so one can, containing 35 is 1.2 standard deviations above the mean. All right. So they're telling me the Z is 1.2 standard deviations of the mean. So approximately what percent of 8-ounce cans of cola have a content greater than 35? Oh, well, this is 1.2. Excuse me, 1.2. So they're just asking for this area right here. Well, it's like, hey, I can go, since I have a Z-score, I can go directly to the calculator. I can do a norm CDF. Lower is going to be 1.2. Upper, it could be huge. It could go to positive infinity. Mean of all Z-scores is 0. Standard deviation is 1. And you're like, how did you know that? How did you know that you could take the shortcut? And it says, is 1.2 standard deviation. And the Z-score is the number of standard deviations. Don't forget that. So second bars, norm, CDF, lower bound 1.2, upper bound 9.99, mean is 0, standard deviation 1. And we end up getting 0.1150. And when I look at my answers, the best answer is 12%. All right. Moving on. Number 9. The probability of obtaining a head when a certain coin is flipped is about 0.65. Which of the following is close to the probability that heads can be obtained in 15 or fewer times when the coin is flipped? 25 times. All right. So they want 15 or fewer. So we want the probability that x is less than 15. So we want all of those values. And they tell us P equals 0.65. We're flipping it a total of 15. I mean, we're flipping it 25 times. So we have a fixed number of times that we're flipping it. So this is a binomial. It's a CDF because it's multiple values. So 25 to 0. Probability of success is 0.65, 0.65 to the 0. Then 0.35 or 1 minus, and this is just the 1 minus 0.65. 25 minus 0 is 25. 25 choose 15 because we want all 15. 0.65 to the 15th, and 25 minus 15 is 10. So this is going to be a binomial CDF trials equals 25. P is 0.65, and our highest x value is 15. So when I go to the calculator with this, second bars, binomial, CDF, trials, 25, probability of success, 65, x value, 15, and we end up getting 0.3696. And our closest answer to that is B, or 0.37. Okay. A certain type of remote controlled car has a fully charged battery at the time of purchase. The distribution of running time in cars of this type before they require charging the battery for the first time after this period of initial use is approximately normal with a mean of 80 minutes. All right, so here's my 80 minutes. And a standard deviation of 2.5. All right. Well, if I add one standard deviation, mean plus one standard deviation, this will take it to 82.5 because I just added the 2.5. Then that's 80 plus one standard deviation, and 80 minus 2 times that. So 80 minus 2 times the 2.5, and that 80 minus 2 times 2.5, and that's 75. And this is 82.5. So in this case, it's telling me that it's going to run between 75 and 82.5. Well, that's A. All right, because its initial use is between 75 and 82.5. This is the 75. This is the 82.5. And by the way, you need to draw the incomplete normal curve and label it out as I have on this one. Okay, so that's number 10. Number 11, in a large set of data, they're approximately normally distributed. Okay, so they're normal. That means I get to use the normal distribution properties, normal areas. Has a z-score of -1. Well, what's a z-score of -1? So well, let's deal with the easy ones. S is the first quartile, so that means that's 0.25. This is the 20th percentile, so 0.20. So T is going to be smaller than S. Now I need to figure out what -1 is. Well, remember, z-scores have a mean of 0, and this is -1. So I'm looking for this area, which means I can do a norm CDF lower equals -infinity, upper equals -1, mean is 0, standard deviation for all z-scores is 1. So let's go to the calculator. Second vars, norm CDF, -9.99, upper -1, mean 0, standard deviation 1. And I end up getting that this area right here is about 0.3413. All right. Drop my pen. So what happened there? Go back and check that. Second vars, normal CDF, 9.99. There we go. I'm having trouble. -9.99. There we go. Make sure you have the negative sign in there. And so we end up getting a value of 0.1586. I knew I had a problem as soon as I had that negative values. I can't have negative probabilities. So -0.1586. So 15%, that's my smallest. So that means, and they said, which is it from least to greatest? So R is my smallest at 0.1587. T is 20%, followed by S. So RTS is right there. Okay. All right, number 12. A recent study was conducted to investigate the duration of time required to complete a certain manual dexterity test. The reported mean was 10.2. Okay. With a standard deviation of 16. Suppose the reported values are the true mean and standard deviation of the population of subjects in studies. If a random sample of 144, we have a random sample of 144. That's important. Is selected from the population. What's approximate probability the sample will be more than 11 seconds? Well, they didn't tell us the underlying distribution is normal, but we're talking about the mean. And since we're talking about the mean, Distribution of the means is normal by central limit theorem for n greater than or equal to 30. So we're going, okay, normal by central limit theorem. And they said, well, remember the mean is the mean is the mean. So we're going to be centered at 10.2 because that's the actual mean. We have a standard deviation of 16. And they want to know its probability of having it greater than 11. So they're looking for an X bar of 11 or more. So we want the probability that X, this should be an X bar, should have a line over it, is greater than 700, which is the probability of Z being greater than 11 minus 10.2. It's normal by central limit theorem. So remember, we're going to have 16 divided by 144. And so I need to go stat test Z test, stat test Z test. Mean is 10. Standard deviation is 16. 11 is my X bar. Sample size 144. Calculate. We end up being the probability Z is greater than 0.75. So we want the probability that Z is greater than 0.75. And that equals 0.2266. Let me go back to that. I think there's an error. So stat test, Z test, 10, 11. Oh, 10.2, 10.2. That's my problem. This is 10.2. Oops. Stat test, Z test, 10.2, standard deviation of 16. Now we get going. All right, so 0.27. So we want the Z score of 0.6. Probability that Z is greater than 0.60. That's the nice thing about a multiple choice is I can sit there and go, oh, I don't see my answer. So I can go back and check it. 2.7422. All right. Now we need to remember this can be written as a norm CDF and it can be written two ways this way. And so we're going to do both of them. Lower bound equals 11. Upper bound, positive infinity. Mean is 10.2. And the standard deviation of X bar is 16 divided by the square root of 144. Or norm CDF, lower equals our Z score of 0.6. Upper is our Z score of positive infinity. Mean is 0. Standard deviation is 1. That's the parent function. And I'll go ahead and run that for you just to show you. Second bars, normal, CDF, lower, 0.6, upper, 9.99, mean is 0, standard deviation 1, 0.2742. Okay? All right, moving on to number, so that was number 12. And our answer for that one would have been B. Made that easy by not having an E. Number 13, based on the values of the true mean and true standard deviation, it can be concluded that the population distribution is not normal, and therefore the probability cannot be calculated a distribution of test certificate, which is the following is estimate of the Z-score of the third quartile. Well, if it's not normal, then we can't do it. All right, so specifically speaking, we can only use the normal numbers of the normal Z-score associated with Z-scores. Now, you can calculate a Z-score of any distribution, but you can only assign normal probabilities if the distribution is normal. It could be normal because the underlying is normal, or it could be normal because the distribution of means is normal, approximately normal by central limit theorem. But in this case, they just say, hey, the it's not, the underlying distribution is not normal, so we can't do it. All right. Number 14, a distribution of scores is approximately normal with a mean of 78. Here we go. Once again, drawing our picture. Which of the following can be used to find the score X above which 33% of the scores falls? Remember, we draw an X and we go, oh, is the 33 above it or below it? Well, they're telling it's above it, so that means our 33 is up here. All right. So if that's 33, this is going to be 1 minus 0.33. And so I'm going to need to find the z-score associated with that value. All right. Well, so I need to do a second vars, inverse norm, area equals 0.67 or 1 minus 0.33, and mean equal to 0, standard deviation equal to 1. Second vars, inverse norm, 0.67. We end up getting 0.4399 as my z-score. And once I plug in, it's like, oh, 0.44 is x minus 78 over 8.6. A lot of people chose 0.33 or 0.67. And remember, first off, x, and it says above. Very important to put the 33 above. I write down z equals x minus mu over sigma. I start plugging in. It's like, well, I have my mean. I have my standard deviation. I'm looking for my x, stalker. And I do the inverse norm, and I'm working from the left. So this ends up being the 0.44 because we're above it. And that gives me that value. Hope this helped. And we'll see you on the next one. Thank you for watching.